as mentioned in the previous video, my plan for this video is to talk about how refraction can be put to use to make lenses. So by the end of it you should be able to tell me what the two types of lens are and draw and interpret ray diagrams for a couple of different situations. So if we review what we learnt about in the last video, which was refraction, we said that waves can change direction when they enter a material which changes their speed. So in the case of light, when it goes from air to glass, or air to water, or air to plastic, transparent plastic obviously, then the wave slows down and changes direction, which is what it's doing here. So the wave's coming in, it's slowing down and getting closer to the normal, the angle's less here. When it exits the material, the opposite happens and it speeds up and it deviates the opposite direction. So refraction is due to the wave changing speed, and all waves can refract. We also looked at prisms, and we introduced the idea that white light is a combination of all the different colours of the spectrum, and when white light goes through a prism then it is dispersed and we end up with the colour spectrum from red through to violet on here, and you should be able to tell me the order of the colours. Right, so let's look at how we can use that for lenses. If we take a triangular prism pointing in this direction and we shine some light in this direction, then it will refract. I haven't put the normals in, by the way. It will refract in this particular way towards this point over here. Similarly, I can do the inverse of that. I can flip it up the other way and this ray of light will also refract to this point here. And then in the middle we've got a rectangle, and any light that goes through at 90 degrees to the material surface, i.e. 0 degrees angle of incidence, because remember we measure from the normal, which is at 90 degrees, to this surface here, goes straight through and also ends up at this point. Not every ray of light will go through and hit this point, because of course I can draw a ray of light starting here and going in this direction. Whoops, very badly drawn, but you get the idea. And of course as it goes straight through, it would miss this point here. Okay. Similarly, a ray of light travelling from here, again very badly drawn, would end up coming through parallel to this one and ending up over here. So there's a big gap over here. Okay, so the way we get a lens to focus every ray of light to the same point is not to have straight lines, but to curve the lens like this. So a lens is basically a piece of glass or plastic, or in fact any transparent material. Most lenses are made of glass or plastic, which is shaped like this. When you look at the side, if you look at it from the front, it most likely will be a circle. Okay, but we're looking at it from the side, and it bulges out in the middle to make that curved shape. And every ray of light coming through then is focused to a single point here. So that's the first type of lens. The other type of lens curves the other way and gets thinner in the middle, and the rays of light, instead of coming to a point, spread out. We'll look at that in more detail in a moment. So the two types of lens are called convex and concave. Now the way I remember which is which, if you imagine a rock face, then a cave goes into the rock face, and so concave lenses go in. You might also see them called converging and diverging, and that's describing what they do with the rays of light. So rays of light going through a convex lens will converge to a point. Rays of light going through a concave will diverge away from the centre point. So you sometimes see them called converging lens and diverging lens. It means the same thing, but you will just be aware of the different types of name. Now in science we're generally quite lazy and we don't like drawing all of this every time, and we draw lenses more like this. Okay, so this line, the vertical line, represents the centre of the lens, and we imagine that all the refracting happens there, which is fine. If the lens is thin, that's perfectly acceptable. If I dot this in, you can imagine that the lens continues there and there, I've drawn that badly again, and then here also you can imagine that this curve continues, not as obvious on that one, but you see that this curve continues that way, and we end up with the shape of the lens. So that's why we use those. They look like arrows, but they're really showing you the shape of the lens at the ends of the arrow, at the ends of the line where the centre of the lens would be. Right, so let's have a look at how we draw ray diagrams. This is quite a complex idea. So let's start by drawing our lens. So we've got a convex lens or a converging lens. Remember that shape. And I've also drawn in what's known as the principal axis. These points here are a set distance away from the lens, and that depends on the power of the lens. So a more powerful lens will have these closer, and that distance from there to there is known as the focal length of the lens. If you're into photography, you might have come across the term focal length. A longer focal length makes further objects appear bigger in your viewfinder. So these points here are known as the principal focus. Or foci, because there's two of them. And as we saw, any ray of light which is passing along in this direction, should be straight obviously, will come down and pass through that point. So any ray of light passing in this direction parallel to the principal axis will come through the principal focus on this side, and similarly this way as well. I'm only drawing it one direction, but it works both directions, so that will go through the principal focus on that side, and so all that, and so on and so on. That's drawn very badly, but hopefully you'll get the idea when you see the next images I'm going to put up. I've still got my lens with the principal axis and my two focal points, or principal focus, and I've added an object which I'm going to look at, and I'm going to view that object through the lens, and an image will form somewhere that I will be able to see. Now, we learnt in the very first video that I did on light that we observe things because light is being scattered from objects in all directions, and some of them end up in our eye, which means we can see it. So light from some other source, in this case probably the sun, will be hitting the tree and scattering off in all directions, and one of those particular rays happens to be going in this direction parallel to the axis. Now we've just said that any ray of light that does that will go through the principal focus. So we end up with that. That's fine. So that means our image is going to be somewhere along this ray of light, but I don't know where yet, so I need a second ray. And the next easiest one to draw in is one that comes from the same point and passes through the centre of the lens. Any ray of light that passes through the centre of the lens will go straight through, undeviated, near enough. Again, that's fine if we've got a slim lens. So where they cross, that is where the image forms. So we'll see a tree in this point here. Now you'll see it's upside down because we started out with the rays coming from this point and ending up at this point, which is now below the principal axis. So when we look through a lens of this type with an object a distance away, we see an upside down object, and you'll also know it's smaller. So we use particular words to describe the image that's formed. So in this case it is diminished because it's smaller. Okay, that means it's smaller. It is inverted, which means it's upside down. And it is real, which means that if I was to place a screen here at the point where it crosses, then I'd get an image of the tree forming on the screen. These rays of light that pass here actually do pass here, and I haven't had to do anything fancy, you'll see in a minute, in order to work out where the image is. Okay, so that's a real image. So we always need three terms to describe an image that's formed in a mirror or in a lens. If I do the same sort of thing, but instead of putting the tree over here, I put it closer, it probably wouldn't be a tree because you wouldn't have a lens big enough, but you get the idea. Then the image that's formed is different, and we still need to describe it with 3 terms, but we're going to use 3 different terms. So again, we need ray of light from some point. Usually we pick the top because then we know where it is. Parallel to the axis is the first one we draw, goes through the principal focus. Then we take from the same point through the centre, goes straight through. They're not crossing, so we've got no image, except we do. What we have to do is we have to dot these lines back and work out where they would have crossed if they'd come from over here. Okay, so you can see I've dotted these lines in because these are not actually rays of light. They're called virtual rays. They don't exist. There's no light coming from this point here. It's coming from here. It's just when we look through the lens, it appears that they came from here. So we end up with a virtual image. If I put a screen here, I wouldn't get an image formed. There's no rays of light there. Our eye can see it because the rays of light enter our eye and get focused, and it appears to have come from back here. Okay, so this is a virtual image formed by virtual rays because our eyes are focusing real rays, making it look like it came from here. Right, now, how do we describe this image then? I've already said that it is a virtual image. We said the previous one was a real image, so we've got real or virtual. This one's virtual. The previous image was diminished in size because it was smaller. This one's enlarged because it's bigger. And the other one was inverted, meaning it was upside down, and this one's the right way up, so we say it's upright. Okay, so you've got a choice of enlarged or diminished, upright, inverted, virtual, real, and you can have a number of different combinations of those depending on the lens type and the position of the object. So on to magnification. So take the example we've just done. We said we've got a virtual image formed at this point here from an object that was at this point here. And the virtual image was bigger, enlarged, compared to the object. Now, if I measure the size of the image and the object, I can work out how many times bigger it is, and that gives me the magnification. So in this case, using my ruler, the image height is 3 centimetres or 3 metres or whatever happens to be. And as long as we use the same units for either of those, it doesn't matter what units we use. Divided by the object height, which in this case is 1.5. So 3 divided by 1.5 equals 2. Now there are no units for magnification because we're dividing a height by a height, so the units cancel out. So the magnification of this particular lens is 2. That means in this orientation the image is twice as big as the object. Let's look at the other example we did where the image was diminished, smaller. So in this case our magnification is the image height, which is around about 1.2. So magnification equals 1.2 divided by the object height, which is 2, and that equals 0.6, and again there are no units. So because we've got a number that's less than 1, that tells me that the image will be smaller than the object. If you've got a number bigger than 1, then the image is bigger than the object, and obviously a number that is exactly 1 means the two things are the same size. And that's it for this video. Thank you for watching.